Hi, so today we're going to prove Leibniz theorem by induction. That's the result given below, which is the formula for the nth derivative of a product of two functions. And we are going to assume the product rule for this proof. Now, before we start, there's a couple of results which we'll be using in the proof, and I'll talk through those preliminary results first. So first thing is this, and if you've got some function, say, and you've got a series, and you were to shift the limits up by 1, so I'm going to add 1 to the bottom end and the upper end, so that is, instead of k starting at 0, it starts at 1. Then I shift it by 1 in the upper limit, so I've just shifted everything by 1, and I adjust for that by taking away 1 each time. Then it's exactly the same. So I haven't changed anything, I've just changed the limits. This will be a useful property which we'll be using in our proof, and I'm just going to give a very concrete example of how this actually works. So let's look at this. Say f of k was 2 to the k plus 1. Let's say something like that. Now let's see what happens when we find, say, this sum. So we put k is equal to 0. We're going to get 2 to the 0, which is 1 plus 1. That leaves us with 2. And then we put k is equal to 1. So 2 to the power of 1 plus the 1 gives me 3. K is equal to 2. 2 squared is 4 plus the 1 gives me 5. And finally, 2 cubed is 8 plus the 1 gives me 9. Okay, so that's using this. Now let's see what happens when we use the same series, okay, but shifted everything up by 1 and then changing it. Instead of 2 to the k, where I see k, I'm going to replace with k minus 1. Let's see what happens here. So if I did that, I'm going to have, now we start at k is equal to 1. I've shifted from 0 to 3. I've shifted everything up, but I've made up for it by changing this, you see. So when k is equal to 1, I'm going to get 2 to the power of 1 minus 1, which is 2 to the 0, which is 1 plus the 1, that gives me 2. And we can see already what's going to happen without going through too much detail. K is equal to 2. That's going to be 2 to the 2 minus 1. So that's 2 to the power of 1, which is 2 plus the 1 gives me 3, and so on. So we can see that this, and it makes sense that if we shift this up by 1 and then make up for it, so we shift the limits by 1, but then we make up for it by taking away 1 here, we get exactly the same series. And now let's say, for example, it's a derivative. So let's say this represents a derivative. So let's look at this one here with k is equal to 0. So that's the 0 derivative of f. So that's just f of x, really, isn't it? And then when k is equal to 1, it's the first derivative, 2 second, third derivative. Now let's see if that's the same as this. Okay, so now we're going to adjust it. So instead of starting at 0, we're going to start at 1, and we've got k is equal to 1, and that again gives us 0 here. Of course it does. And as we can see, as we move along, we get exactly the same. So if I replace here k with k minus 1 and I shift my limits up, I get exactly the same series. And that's just a very simple observation, but important for the purposes of our proof. And another thing we note is, supposing we had this. Now this is the binomial coefficients. So supposing we had n choose k minus 1 plus n choose k. And just to remind ourselves that this is the NCR formula. Okay, now let's see if this result is true. Let's see if we can go through this result. So just by using the formula that n choose k minus 1 plus n choose k. So let's use this. So we're going to have, on the top, we're going to have n factorial. R here, instead of r, we've got k minus 1. So what's n minus k minus 1? It's going to be n minus minus 1 becomes a plus, and then just k. So instead of r, we've got k minus 1. So n minus bracket k minus 1 becomes n plus 1 minus k factorial, and then instead of r, again here we've just got k minus 1. So just using the standard formula for the choose function, we have this. And similarly, this is just exactly as that is, but with k instead of r. And now we observe two things. That firstly, if we focus on this, we can say that that is the same thing as n minus k factorial times n plus 1 minus k. Okay, so this number, remember these are integers, so this is just one term along. Okay, so this is just this number but plus 1. And I can give a very concrete example of how this works. In fact, before we do that, let's look at the next one. It makes even more sense. Let's look at k factorial. That's just going to be k minus 1 factorial times k. Okay, and this is just the same principle, but now with n minus k, sorry, and then n minus k plus 1, the next term along. And let's have a look at how this result works. Let's say we had 4 factorial. Okay, that's 1 times 2 times 3 times 4. But that's the same as saying that's 3 factorial times 4. Okay, that makes sense. Okay, so here k factorial is the same as k minus 1 factorial times k. Makes perfect sense, just from the definition of factorial function. So we need to have a look at this and have a think about how it would work before we move on. Pause and have a think. So next, let's look at what the lowest common denominator is. Okay, so we can see that k factorial and k minus 1 factorial, k factorial is bigger. So for this one to be the same as k factorial, I just need to times this by k. And n minus k factorial and n minus k plus 1 factorial, this one's going to be bigger. So top and bottom of this one, I just need to times by n plus 1 minus k. Okay, so this one times this will give me this. So top and bottom of this, I just need to times by k, and top and bottom of this, I just need to times by this to make this times k factorial the lowest common denominator. So that's what I mean. Okay, so when I combine the fractions, this is just making the denominators the same, and I'm combining the fractions. So this left one, I just need to times by k, and this right one, I just need to times by this. And now we can see that we've got n factorial as common on top, so we can factor that out. And we have this. But what is that? That's just n plus 1 factorial, isn't it? Just using this result, really. It's just n factorial times n plus 1 is the same thing as n plus 1 factorial. And now let's look at what we have here. Where we see n, we've got n plus 1. Where we see n, we have n plus 1. So in other words, this is exactly, just from the definition, just n plus 1 choose k, which is the right-hand side. So we've shown that the left-hand side leads to the right-hand side just from the definition of factorial, nothing more than that. And from the definition of the choose function as well. Okay, so we've established these preliminary results. We can now move on to the proof. Now, as with all proof by induction, we need a basis. And for that, that's when n equals to 1 is our base case. So it's going to be k is equal to 0 to 1. Okay, so n choose, let's go through each step. N choose 0, 1 choose 0. Remember, this is the base case, so we're going to put n equals to 1. Okay, so it's going to be 1 choose 0, anything choose 0 is 1. Then we're going to replace k is 0 here. That's our first term of the summation. So that's the 0 derivative. So that's just f of x times n is 1, k is 0. So it's going to be g of x. And then when we move on to n is 1, we're going to get, we move each term. So here it's just f of x, and here it's just n1. So it's just the first derivative of g. Okay, k0. That's our first term. So we're going to get this. And now when we put k is 1, 1 choose 1 is still 1. And then we're going to have the first derivative of f. Then here it's going to be 1 minus 1, which is 0. So it's the 0 derivative, which is just g of x. And this we can verify is true because that's just the product rule, which we can assume. So it's true when n equals to 1. So we have our basis. Okay, and this rule we haven't proven, but we're going to assume for the purposes of moving forward that the product rule holds. And therefore this is true for the case n equals to 1. And our basis is covered. Now we're going to suppose true for n equals to r. Okay, so what does that mean? So we're going to assume the following is true, that the rth derivative, if we like, or is true, and this formula is true when n equals to r. Okay, so we're going to assume that. And then what we need to show is that this implies that f of r plus 1 becomes this. Remember what we need to show always in proof by induction, that usually it's k, but I've used the letter k here. So the truth of k implies the truth of k plus 1. In this case, it's just the letter r instead. So it's the truth of r implies the truth of r plus 1. So where I see r, I replace with r plus 1. Where I see r, I replace with r plus 1. So this is what we assume, and we know what our target is. We know what we need to get to. As with all induction problems, we always know what result we're trying to show. Doesn't mean it's easy to show, but at least we know what our target is. Okay, so here's our assumption. And now we know that the next derivative must be the derivative of the previous one. Okay, so the r plus 1 derivative is the derivative of the r derivative, rth derivative. Okay, and what exactly is that? Well, that's the derivative of this, because we know we've assumed that this is true, so we're just going to differentiate this with respect to x. Okay, so let's just focus on this derivative. Now I'm just going to write down some of the terms here. So let's just write down a few of the terms. We can see that the next derivative is the derivative. So let's look at it. We start with k equals 0. This is just a formula with k 0. Then k is equal to 1. That's what this means. Okay, it's a summation. So we just substitute in where we see k. We replace with 0, then 1 all the way up to r. I haven't written it in, but dot, 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 all the way up to the last term. And if we stop to 1, then it will be r choose 1, f 1x, g r minus 1, just following the formula. So we stop to m, okay, some number along this journey from 0 to r, then it's this, okay? So as it varies, okay, now let's look at each one in turn. What is this? Well, this is a coefficient, which is a constant, okay, binomial coefficient, and a product. So we're differentiating a sum, okay, we've got a series, a sum of different terms, each of which is just a product, okay, times by a constant. Again, r choose 1, it's just a constant, it's just r, okay, times a product. Okay, a constant times a product. So let's look at each of these derivatives. Well, this is just, I can factor out the constant, and what do I have? I've just got the product rule, which we can assume. So here, okay, it's going to be the derivative of this. Remember, when it's 0, it's just f of x. So the derivative of f(x) times this plus this times the derivative of this. Okay, but the derivative of this is just g r plus 1. It's just the next derivative. And similarly, let's have a look at this. Similarly, we can factor out the coefficient, and we're going to take, using the product rule, it's the next derivative. Okay, so that's the first derivative. We're going to differentiate again. It's just the second derivative times this one plus this times the next derivative of this. But when you've got minus 1, so you add 1 to it, you're going to get gr, etc. And what about here? What would that be? So you can pause the video and have a think, but we can see similarly we factor out the coefficient and we take the next derivative, Okay, so it's going to be fm plus 1. Okay, that's the next derivative of this times this one. And then it's going to be this one times the next derivative of this. And that just is represented by just putting a plus 1. That just represents the next derivative and so on. And so this is what would happen if we were to differentiate each term. And there's another way to write this neatly. And using this, if I stop to m, it's here, okay? It would be this. So as k varies, okay, let's look at this. It's exactly the same thing, but now I've just put it as k. So as k varies, as k goes from 0, we have this, plus when k is equal to 1, okay, I'm just replacing k is equal to 1. We have this, and at some other point, m, it's just this, and 2, 3, 4, 5, all the way up to r. So in general, each of the terms in our sum, each of our derivative, can be represented nice and neatly using sigma notation as the following series, as k varies from 0 to r. Okay, so you can pause and have a think about that. Now the next thing we're going to do is we've got a sum, okay? So we can split this up like so. Okay, so we've got a series with an addition in between. So we can split it up into the sum of two separate series, just splitting this and this one up. Next, we are going to use the result which we showed at the beginning, this result here. So this is fr plus 1x, which has led to this. Okay, we've just got to this stage and we're going to use this result. So let's look at how we're going to use this result. So we've split it up into the sum of two series and we're going to use this result. So here for this left one, I'm going to swap my limits. So I'm going to add 1 to the bottom and the top end, but then I change where I see k, I'm going to take away 1 from k. So k plus 1 minus 1 is just k. R minus bracket k plus 1, minus 1 rather, the two minuses makes it a plus, okay? So where I see k, I replace with, in brackets, k minus 1. So I end up with this. So just this and this, as we've shown at the start, are just two ways of representing the same series. And this we just leave alone for now. Now, what I'm going to do is we're going to focus on this one, and I'm going to just extract the last term. What do I mean by that? So where I see k, I'm going to replace with r plus 1. Okay, so I'm just going to take out the last term of this series. Let's see what happens when we do that. So I'm going to extract the last term. So we've got r plus 1 at the top. I'm just going to take out the r plus 1 term and separate it. So it's going to be the sum up to r plus the final term of the series, which I've just plugged in r plus 1 directly. So it's going to be r plus 1. Where I see k, I put r plus 1. So it's going to be r, choose r, which is 1. Here, where I see k, I replace with r plus 1. Where I see k, I replace with r plus 1. So it's just going to be this. Because I've got bracket minus in bracket r plus 1. So the 1's cancel out and the r's cancel out. And I'm left with g0, which is just the function g of x. So here I've extracted the last term, the r plus 1 term. So I'm left with the sum up to r plus the last term separately. Okay, and here we're going to do the same thing. We are going to extract not the last term, but we are going to extract the first term. So I'm going to go from 1 to r, and where I see k, I'm going to replace with 0. So before I continue, let's see if you can see what's going to happen next. So I'm going to go from 1 to r, and then I replace k with 0. So r choose 0 is 1. When I replace k with 0, I end up with this. I replace k with 0, I end up with that. So I've extracted the first term of this, okay? So we end up with this. And now let's look at this. Before we move on, we notice that we've got a series. same limits, same function inside. Everything is identical apart from the coefficients, which are just constants. So we can combine the two terms inside the brackets. Okay, so have a think about that, but we can just pull it out, and those two terms, so I'll say it one more time, this and this can be combined to become this. Okay, everything is identical, and we have this separately. And now we use the second result that we showed at the beginning, which is, if we notice here, we're going to replace this with this result. We end up with, I'm using this result, so I end up with this. Now here's a nice little step. What we're going to do is we are going to now bring these two terms back into this summation. How do we do that? Well, let's look at k. Let's focus on k. Okay. Now you imagine that if I put k is equal to 0, what do I end up with? R plus 1 choose 0, that's just 1. Okay, anything choose 0 is 1. K is equal to 0, well, that's just fx. K is equal to 0, that's just gr plus 1. That's just this. Okay, with k is equal to 0, so it's just this function. But where I see k, I put 0. So I can put this into here and change this from 0, and this could be included in this. Okay, and similarly, let's see what happens when I put k is equal to r plus 1. Okay, so we're going to have r plus 1 choose r plus 1, and the rule we know is n choose n is always 1. Now I see where I see k, I put r plus 1. Look, that's what I have. Where I see k, I put r plus 1. Well, that means I end up with 0 here, so it's just g of x. So here, I can now bring these two back into the summation. Okay, so this one is where I see k is equal to 0, and where I see k is equal to r plus 1, I have that. So these two separate terms can be brought back into the series, okay, as given. Okay, so this is when k is equal to 0 into here. So, and then this one is when k is equal to r plus 1. So I'm bringing these two, and I'm writing everything neatly in here. So k is equal to 0, which is this. K is equal to r plus 1, which is this. And that is exactly the result that we're trying to prove. Because if we go back to the beginning, this is exactly what we were trying to prove. Okay, but where I see r, I have r plus 1. And therefore, we can now conclude that, therefore, true for n equals r plus 1 if true for n equals to r. And since it was true for n equals to 1, this implies that it's true for all n belonging to the set of natural numbers. So all natural numbers n must be true. And that's the end of the proof. So there's a few sort of tricky bits along the way, but you can watch the video again to see how each one works. I hope you enjoyed the proof. And that was the proof for Leibniz theorem by induction.